Select the major product of the following reaction. So if we look at what we are given in this problem, we see that our reactant here is a Grignard reagent. And we know that Grignard reagents are really strong bases and really strong nucleophiles. So if we're taking a look at what we're reacting it with, we see that we're reacting this with carbon dioxide. So here is the general structure of carbon dioxide, and the carbon in the center here, if we cover up one side, we see it looks kind of like a carbonyl, and we can add to the carbon of carbon dioxide the same way we would add to a carbonyl. So we can draw our Grignard reagent, and I'm going to count the carbon atoms of the Grignard. So I can see I have 1, 2, 3, 4, 5 carbon atoms, and this one that I've labeled number 5, that's not an IUPAC numbering, I'm just numbering to keep track, that's attached to the magnesium, that's going to be a nucleophilic carbon because you've got a partial positive charge on that magnesium and a partial negative on that carbon. And if you want, you can actually draw that as a full anionic charge just to make it a little bit easier to see what is happening. So I'm going to draw 5 carbon atoms. And so this last one is where I'm going to represent it as an anion with the magnesium bromide as the counter ion. So in truth, this is a very, very polar covalent bond, but drawing it this way allows us to see very clearly that this is the carbon atom that is nucleophilic. And so that is the carbon that's going to attack our electrophilic carbon of the carbon dioxide. So if I draw this arrow, I can see that it's attacking the carbon, and then we are going to break one of these two bonds, either pi bond, it doesn't matter, they're completely equivalent. So I'm going to put these electrons down here, and we're going to draw the result of this. I'm going to see the 5 carbon atoms that came from that Grignard. So I'm going to go ahead and put it into skeletal structure now. So 1, 2, 3, 4, 5, and then I have a new bond to the carbon of that carbon dioxide, and it still has a double bond to one of the oxygens and a single bond to the other. And so we see that we now have this carboxylate ion, and there's no way to kick off a leaving group. The only thing you could possibly imagine is it going backwards and kicking that off, but that is absolutely not going to happen because that starting anion is just way too strong of a base to act as a leaving group. So nothing is going to happen. This is going to sit here as that carboxylate ion until you go to your second step and add in that acid. And so once we do that, so we've got some aqueous acid. So what's going to happen when you add in that aqueous acid is your carboxylate is going to grab a proton so that you will get as a product a carboxylic acid. So we can draw that carboxylic acid. So I'm still highlighting that new bond as a green bond, and we've got the carboxylic acid. And so you can see we have 2 options here that are carboxylic acids. We just want to make sure that we're counting our carbons correctly. So we started with 5 and we added 1 more. So we should have in total 6 carbon atoms. So let's go ahead and make sure that we do. And then we want to pick the option that has 6 carbon atoms. So it looks very much like D to me. So let's go ahead and number this just to check. Yes, and we see those 6 carbon atoms. And if we look at A, there's only 5. So this is really an exercise in making sure we can form the right bond, see what functional group we're forming, and make sure we're keeping track of all the carbons. That we started with 5 and we added 1, so we have this 6 carbon atom carboxylic acid as the product.